Welcome back to Chemistry for Engineers, Chem 131 at SMCC with Jennifer Chamel. And today we're going to be talking about Chapter 7, and that's chemical bonding and molecular structure. So this is going to be our Lewis dot structures and molecular geometry and shape and things like that. All right, so first of all, we're going to be talking about a couple different kinds of bonds. One is covalent bonds, and in covalent bonds, we lower the energy of the molecule by sharing electrons between two nonmetals. And in ionic bonding, we lower the energy by transferring electrons from a metal to a nonmetal. So the lower the energy, the better. It's kind of like an energy well where you settle in. And so in ionic bonding, you have that transfer of electrons, that give and take. The metal gives electrons to the nonmetal. And then in covalent bonding, you have sharing between two nonmetals. Okay. So now let's take a look at, I'm going to try to keep track of my pages here. Okay. And here is slide 3. Okay. Now what we're doing is we're looking at our chemical bonds. Okay. So during ionic bond formation, the cations and anions achieve this NP6 electron configurations. Sometimes you'll also see that as S2, NP6 for any of them. And if you remember from the last chapter, that is your full row right there. And N again is that energy level. So that might be, for example, if it's neon, it would be 2s2, 2p6, and that's neon's valence. Okay. All right. And then, so we have a couple of rules that we're going to be working with here. The first one is our duet rule. Now, if you remember, in n is equal to 1, you just have a 1s orbital, and that just has 2 electrons. And that's basically just hydrogen and helium. Okay. And they are going to be stable with a 1s2 configuration. And so they only share 2 electrons. Okay. Now our next one in here is our octet rule. And this is where atoms form covalent bonds to share 8 valence electrons. And that's because when we get beyond that, remember that 2s2, 2p6 for the valence, that's 8 electrons. Okay. Or 3s2, 3p6, that's 8 electrons. And that's what we would call a full octet or a full valence shell. It's also a noble gas configuration. And that is how we are most stable in there. Okay. All right. So basically, yeah, I said that. Okay. All right. Moving on to slide 4. Okay, now let's take a look at what we have here. I'm going to go ahead and I'm going to switch to just a completely separate color. Lewis dot symbols or Lewis dot structures place valence electrons that allow the prediction of bonding in molecules. Okay, and to draw a Lewis structure, the valence electrons are represented by these dots. So for example, if we were going to be working on that hydrogen, which we had before, has 1 electron, and we're just going to put it right there. Okay. And that's its only valence electron. And it has basically 1 spot for bonding because electrons like to pair. So this shows you it only is going to form that 1. So now what we can do is we can look at the molecules, the atoms, that we have down here. And these are the atoms in the energy level 2 shell. And they're going to be, it's going to be pretty much the same. Now, lithium and beryllium, lithium is an alkali metal. So it's going to lose this electron. Okay. So it's going to lose this electron. I'm having trouble there again. Okay. So it's going to lose the electron, and that's going to become Li plus. Now, beryllium is a little bit different. Beryllium's tiny. It can either lose the electrons to become Be2 plus, or beryllium with the appropriate nonmetals can have two sites for bonding and form covalent compounds. It's kind of interesting. Beryllium it's very electropositive, though, very low electronegativity. And so this is only going to happen with some pretty strong things like fluorine or something. Okay. Now, boron has these three electrons here, and we want to pair them. So now I'm showing these squares. And if you're wondering, well, what these squares mean, the square means this is a site for bonding. It's a place to share electrons. Okay, to complete the pair. So boron has these three, okay? And you should be writing these down as well. Now, carbon has 4 dots. And so what we want to do is we want to make a space to pair for each one of these on carbon. So boron here tends to form 3 bonds. Okay, carbon tends to form 4 bonds. Tends to, this is the average, okay? Now, nitrogen has 5 valence electrons, so it has pair up here already, right here, okay? This is a lone pair, and it's going to be localized on nitrogen. And now it has these 3 unpaired ones, so it has 3, it tends to form 3 bonds. Not always, but sometimes. Now, oxygen has 2 unpaired, so it's going to form 2 bonds. Okay. And that means that it has these 2 lone pairs here and here. And I vastly prefer to write oxygen in a different way. And that's going to make a lot more sense when we get into structures. But what I want you to do is I also want you to write oxygen like this, where here's the oxygen and here's a pair. Okay. And here's a pair. And then here's a single and here's a single. And that way you have these 2 little sites for bonding, and they come off at this bent angle. Okay. So think about oxygen like that. That's going to be really helpful. Now, our fluorine has 1, 2, 3 lone pairs, and it has 1 site for bonding. And now notice over here with our neon that it has 1, 2, 3, 4 pairs. It has 8 valence electrons, and so it is going to form no bonds. All right, so you just have a little bit of space here. This is showing the valence electron configuration for basically all of your S block and P block, okay? So let's kind of put in a couple of extra things here. So this is going to be, we'll call this group 1 and group 2. So we could even say 1S and 1 and 2S2. Okay. Now, these are also often called group 3A, 4A, 5A, 6A, 7A, A, and 8A. Okay. So keep in mind these here. You can write this on your periodic table if you want to. Okay. And here see the number of valence electrons. So group 1 has 1, group 2 has 2, group 13, 3A has 3, group 14, 4A has 4, and so on. And remember, helium has 2 electrons, 2 valence electrons, because this row here is our duet rule. Okay, and now you can see those places for bonding for everything. And you'll see that within the group, you have the same thing for each one. Okay, here we are up to slide 6. Okay, now let's take a look at what happens with this. We know that hydrogen has one electron and one site for bonding like this. So basically it can share these two electrons to fill that bond. And we're going to draw it just like this. So that bond right there means two electrons. And remember, that's because hydrogen follows our duet rule. Now, most of our atoms follow the octet rule or obey the octet rule, we'll often say, by sharing our 8 electrons. And one example of that is with fluorine gas. So remember that fluorine had this one little unpaired electron here. And so we can join them here, and then you can see them in one structure like this, and then with a single bond like so. Okay. And what that means is that each one of these fluorines now, so each one of these hydrogens has 2 electrons on it. Each one of these fluorines has 8 electrons. See, there's 8 there on that fluorine. And then you can come over here and say, okay, and there's 8 there on that fluorine. Okay, and that's how they share to form 8, or the octet rule. All right. So now let's take a look here. All right, so here we are up to our slide 7. Okay, now let's talk a little bit about electronegativity and the different types of bonding. So first of all, ionic and covalent bonding form the 2 ends of the bonding spectrum. So what do we mean by that? Okay, so if we're sharing evenly here, a perfect share, and transfer of electrons here. Then here we have covalent, and then it's on this continuum, and here we have ionic. But sometimes what happens is that we don't have a perfectly even share. Ionic bonds will have this perfectly even transfer, but what if we have an uneven sharing? Okay, where one pulls harder on the other one. Well, that's based on electronegativity and bond polarity, okay? So electronegativity is the ability for one atom to draw the electrons close to itself. So if it's very electronegative, it's going to pull the shared electrons closer. If it's less electronegative, it's not going to pull as hard, okay? And that's where you get this uneven sharing. And a bond polarity. And this uneven sharing is going to be called polar covalent. And we're going to be introducing the concept of the dipole on the next slide. So this is an electronegativity chart. You also have this printed in your notes, okay? And this is slide 8. Okay, now you can see where these are. The electronegativities increase. So you can see 1, 1.5, 2, 2.5, 3, 3.5, 4. We don't list electronegativities for noble gases because it's very, very rare that they bond, and only the larger ones. Okay, so as you can see, we increase as we go across the table. And then we decrease as we go down the periodic table here. Let's see if I can write sideways. Okay. So this one is your smallest. And up here we have your the largest. So this should remind you of those trends from the last chapter. If you want to, what many students do is that they'll write these little electronegativities on their periodic table, and you can just focus on your metals and your non-metals and kind of where those are on the continuum. Okay, so you won't be able to see this anymore, but it is on your sheet, which hopefully you are filling in right now. So let's take a look at what this is going to be. All right, now let's look. I mentioned bond polarity. All right, and we are up to slide 9. Okay, and I'm going to pause for about 30 seconds. So electron density is not shared equally when elements have these different electronegativities. Okay, so basically, the more electronegative element experiences an increase in electron density. So that means that we're pulling them closer to themselves and has a partial negative charge. The less electronegative element experiences a decrease in electron density and attains a positive or a partial positive charge. Okay, and this makes this little dipole. So let's take a look at these. So first of all, we have carbon, hydrogen, oxygen, hydrogen, and hydrogen chlorine. So this is not an actual molecule. This is a single bond within a molecule right now, though I suppose HCl is hydrochloric acid. So that one could be considered a full out one, but the OH or the CH is a bond within a molecule. Okay, now based on the chart that we had before, then our electronegativity, and I'm going to abbreviate that EN, so we'll call that electronegativity, just say that's EN to make it a little bit quicker to write. All right, now carbon is 2.5 and hydrogen has an electronegativity of 2.1. So that means that the difference between these two is 0.4. Now, basically, remember we had that continuum. So let me go ahead and give you the continuum. Okay, so basically, if it has a metal, then it's ionic. Just like there. So we won't do that. And then where does it make that switch over? Okay, and I'll just kind of go over here. So if the electronegativity difference is less than or equal to 0.4, then we're going to call this nonpolar or completely covalent. Okay. If the electronegativity difference is greater than or equal to 0.5, then we have a polar covalent molecule. Okay. All right. So now let's go over here. So we can see that this CH is at the very top of that nonpolar range. Now, from that periodic table that we had on the previous slide, our oxygen has an electronegativity difference of 3.5, and our hydrogen has an electronegativity difference of 2.1. So we can see that this one is 1.4. So this one is definitely going to be polar. And now remember, it says partial negative and partial positive charge. So where this would come in is, see how this is 2.1? That means that this hydrogen has a delta plus or a partial positive, and the oxygen here is a delta negative charge. Okay, so what that means is that you draw this little dipole aimed like this from the hydrogen to the oxygen to say that the electron density has moved closer to the oxygen. Now, with a hydrogen, we see before that hydrogen is 2.1, okay? And chlorine on our list is 3.0. So this gives us a difference of 0.9. So this one is also polar, okay? And then that means, in this case, that the 2.1 is less than 3.0. So our hydrogen has a delta positive and our chlorine has a delta negative. And we could draw a little dipole on here like this to show where the electron density is moving. And then if we wanted to go ahead and rank these in terms of increasing polarity, we would say our CH bond is first, and our HCl bond is next, and our oxygen hydrogen bond is last. Okay, because increasing is looking at these electronegativity differences. Okay, so let's keep track of our bonding structures, and we're going to be looking at something called a Lewis dot structure. Okay, and let's go ahead and work through this molecule here. Okay, our first, we have oxygen difluoride. Okay, and our first step here, step one, is to count the total valence electrons in the molecule or ion. So you can go back and you can look at slide 5 that lists all of the different uh, um, valence electron counts, and you'll see that oxygen has 6, and we're adding in, we have 2 fluorines, and each fluorine has 7. So 6 plus 14 means that we have 20 valence electrons. And now our step 2 right here is to draw a skeletal structure of the molecule. So we would just say, okay, well, oxygen is here, it comes first and it's less electronegative, so it's going to go in the center. And then we'll put the fluorines on both of them. Okay. And I suppose that was step 3 as well. So place single bonds between all connected atoms in the structure by drawing lines. Okay. So remember, each one of these single bonds here accounts for 2 electrons. So we've accounted for 4. Okay. So I'm going to come down here for our step 4. And we've currently accounted for 4 electrons, and we need 20. So what we're going to do now is we're going to place these on so that we follow the octet rule. So we've got 4, 6, 8, 10, 12, 14, 16, 18, and 20. And now you can see that each of these atoms has 8 electrons around it, and we have accounted for all 20 electrons. So we don't need to put in any bonds because it's completely satisfied. And then just to review, we can draw it like this, but as a little bit of a look ahead for our geometry, let's go ahead and switch it and draw it like this, because that's going to help us remember that oxygen does not form those linear molecules. It forms a bent-shaped molecule. And now down here, I have a couple of always rules. Hydrogen always forms 1 bond and has no lone pairs. Fluorine always forms 1 bond and has 3 lone pairs. Okay. So now let's practice some Lewis structures. Okay, and we are on slide 11. I'm just going to draw one at a time so that I can use the space and then erase it and draw the next one. Okay, so first of all, we're doing molecule number 1 there, CF2Cl2. And our first step was to count our valence electrons. So we have 4 from the carbon, and 2 times 7 for the fluorine, and 2 times 7 for the chlorine. Okay, so that is 28, and 4 is 32 valence electrons. Okay, now our next step is to place our carbon in the center, because basically for how it's drawn. And now we're going to put the chlorines on one side and the fluorines on the other side. It's a very long reason why we do that, and I can explain it to you in class if you want to know. But whenever you have something like this, go ahead and place them on the sides like that. All right. And now that accounts for 8 electrons. So we have 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, and 32. Okay, so now I've placed all 32 electrons. I am obeying the octet rule for each one, and so I'm done. Okay, now let's look at number 2. Here we have water, or H2O. So this means that we have 2 times 1 valence electron for the hydrogen plus 6 for the oxygen is going to give us 8 valence electrons. Okay. And we have the H2 here and then the O. And so we're going to go ahead and place it like this. And remember that I said that oxygen always forms this shape unless it has a double bond. And then that's a little different, but we'll do that in a minute. Okay. So there's 2, 4, 6, 8. Now I have the duet rule for hydrogen that each has 2 electrons, and we have the octet rule satisfied for oxygen with 8 electrons. And so our water molecule is complete. All right, now let's look at carbon dioxide, and this one's going to be a little different. We have CO2. We have 4 valence electrons for our carbon. And we have 2 times 6 for our oxygen. That's 12, and 4 gives us 16 valence electrons. And we're going to place the carbon and the oxygens like this. All right, now I'm going to change things up just a little bit. And we're going to say, okay, now I have 4 electrons here. Let's go ahead and place our electrons. We'll start on the outside because that's more electronegative and work our way inside. So we have 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay. Now, the oxygens each have 8 electrons around it. And so that octet is satisfied, but the carbon only has 4 electrons on it. And so we need carbon to also have 8 electrons on it. So it needs 4 more electrons. And we're going to do that by taking this pair and moving it in, and taking this pair and moving it in. And so what that means then is that we'll have an oxygen with double bonded to the carbon, double bonded to another oxygen, and we're left with 1, 2, and 3, 4 for our lone pair electrons here, and then 2 pairs of lone pair electrons here as well. And now we have 8 electrons on each atom. All right, now we have this tricky one here. Actually, you know what I'm going to do? I'm going to do methane next, and we'll do the vinyl alcohol last because that one is a little bit more difficult. So let's look at the methane. CH4. Okay, our carbon has 4. And each one of our hydrogens is 1, which gives us 8 valence electrons. So this one is actually really quite simple. The H4 means there are 4 hydrogens on the carbon. And in this case, we have 2, 4, 6, 8. We have 8 electrons already present. There are 8 electrons on the carbon, satisfying the octet rule. There is 1 bond, so 2 electrons on each hydrogen for following the duet rule. And then we are done. So I said that one was easy. All right, now let's look at this last one, this vinyl alcohol, CH2CH. OH. All right, so let's take a look at how that's going to work. Okay, so we have, see how it has CH2CHOH? So one of the things that we learned before is we learned when we were making those organic molecules earlier on a few chapters ago. So what we're going to do is we're going to string our carbons together like this, first of all. Like that. This starts with a CH2. That means that here we are going to have 2 more hydrogens on this carbon, and then this carbon is going to be done. And then this CHOH means that this carbon is going to have an H on it, and then it's going to have an OH on it, like that. And it's going to be done. All right, now let's take a look at what's not full. So I built my structure first. Now let me go back, and I know this is a little out of order, but we're going to start adding these up. So we have 4 plus 2 from those hydrogens, plus 4 plus 1 for that hydrogen, plus 6 for the oxygen, plus 1 for that hydrogen, okay? And that is all going to add up to 18 valence electrons. So let's see where we can place these. So first of all, we have 2, 4, I'll count them tiny here. So here we have 2, 4, 6, 8, 10, 12. Okay, so we have 12 electrons already. So what we need to do now is we need to place some more. Okay, so we have 12, we need 18. That means we have 6 more to place. Well, we know oxygen likes to look like this, right? Okay, so now that's 12, 14, 16. So there's 14 electrons while we're keeping, and 16 electrons while we're keeping track. Okay, now what that means now is that we only have 2 more electrons to account for. But this first carbon, carbon 1, only has 6 electrons on it. And carbon 2 only has 6 electrons on it. So if I have 2 more valence electrons left, and each carbon needs 2, then the only way to finish that is with a double bond. And so now what I've done is I have placed electrons up to 18. Okay. All right. So that was a nice and challenging one. And you know what? I think that is a great place to stop, and we will come back and do some more.